Go for it. Yeah. So good morning. Thanks for inviting me. So I'll be talking today about work with Ran Snitkovsky in the Tel Aviv University, and topic is stochastic approximation of symmetric Nash equilibria and queuing game. Now I'm used to give this talk and generally talks to operations research crowds. So I added a few slides about queuing, but feel free to stop me and ask if the model is not clear, if things are not clear. But anyway, there is a lot of game theory as well. So this should be fine. Okay, so first of all, the motivation. Think of some service system with customers arriving and wanting get service from the system. But customers are strategic, and upon arrival or before arrival, they make decisions. Decisions can be to join the queue or not, or to maybe probe the queue, inspect the real-time congestion, or choose between different possibilities, purchase priority. There are various decisions customers can make. Utility of a customer in such a setting is typically modeled as a stationary expected utility, which of course depends on the strategies of all other customers. Okay, so we'll have some probabilistic model for the system, and given strategies, there'll be a stationary distribution, and customers evaluate this their utility with respect to that distribution, and then want to maximize its utility. And we want to find the Nash equilibrium strategy. The problem, however, is that many such systems are simply intractable. You can't get closed form solutions for the expected utilities, and therefore you need to somehow computationally get around it. And what we do here is basically suggest a procedure, stochastic approximation procedure that stimulates the system and simultaneously evaluate the Nash equilibrium. That's the goal here. Do this for a general class of queuing games. Okay, so the plan for the talk, motivation. I've started, but then I'll continue a bit more and present our general framework and results, and then we'll see. This time permits talk a bit about applications and extensions. Okay, so I promised. Well, I'll talk a bit about queuing. So one of the building blocks of a queue are an arrival process. There's a sequence of inter-arrival times of customers, of jobs, right? And we make assumptions about these inter-arrival times. For example, if the arrivals are if the arrival process is Poisson, then the inter-arrival times are exponentially distributed. If they can be deterministic, and so on. Service times, customers have service requirements or job sizes. But a common assumption is that they are exponential, can be uniform, can be many other things, and system design. How many servers, what is the service policy, is it first come first served, are there priorities, are there routing decisions if it's a network? Yeah, so all of these determine a system. And a bit about notation, so this will appear quite a bit in the talk. What's known as Kendall's notation denotes three, sometimes more, but three main objects. First is denotes arrival, second is service this time distribution and per the number of servers. Okay, so in MM1, the M is for Markov or memoryless, denotes a system with a Poisson arrival process and exponential service time, and a single server. And of course, this Markovian model just you a very simple continuous time Markov chain that you can do whatever analysis you want for. The GM1, for example, denotes general arrivals and exponential service time. General, usually sometimes it can be GI, indicating that these are independent, but the arrivals are inter-arrivals are independent, but sometimes it's just written as G. D for deterministic, and GP1, which we will be talking about quite a lot, doesn't make any assumption about the arrivals and service because they both come from general distributions.
When there's no I, the dependence is implied, or it doesn't have to be dependent.
Yeah, so it's usually specified. And GT1 is sometimes used for independent, and sometimes it's GI1. Here I'll be talking about independent sequences without the I notation. I won't be talking about the other case. But in the literature, it's sometimes quite often the I is omitted. Or if there is dependence, it's specified.
Dependency between what? So
It's between, say, arrival times. The time between arrivals, if they are a dependent sequence. So, for example, if there is some dependence on time, then they may be dependent, or if there is some model with burstiness of customers tend to come in groups, then they may be dependent. But we won't talk about these models today.
K servers, how do you allocate the tasks to server?
So the default in a DDK, less specified otherwise, is every customer joins an idle server if there is one, otherwise they join a single queue. There's a single queue, and then the first server that comes available takes a customer at the head of the line. That's a default again, unless specified otherwise. We'll also talk about parallel systems where you have K servers, but each has a dedicated queue, and of course that behaves differently. Okay, so these are notations, but again, of course, if something is not clear when I present specific models, then let me know. Okay, so let's think about the simplest example, and then I'll continue with an economic model for the MM1 queue. So an MM1 queue is just every exponential time a new arrival enters the system. Service times are also exponential IID, and it's first come first served. Okay, so it just looks like this. Lambda is the parameter of the arrivals, and once in a while someone joins the queue here. There's a service node, and they leave at rate u, and very important parameter is the utilization level rho, which is just lambda over mu, incoming rate over the outgoing rate of the system. Okay, so this is gives you a continuous time Markov chain with a known stationary distribution, and for example, there's a well-known formula for the stationary expected delay of a customer in the system. So this expectation is finite only if the utilization level is below 1. That is, otherwise, right, if lambda is bigger than mu, then this process will tend to infinity. Right? Because basically the server can't handle all the incoming work. But if it is and we call this iteration stable, if rho is smaller than 1, then you have this nice closed form formula for the expected delay. And by delay, I mean social time, the entire time in the system, including their own service. Okay, so this includes both waiting in the queue and getting service. So this is the time customers spend in the system. even more than that, W is in fact the exponential random variable in this model. Right, and the expectation is, of course, is a very non-linear property, right? And as it tends to grow to one, as rho tends to one, it basically explodes, and this is it won't be the focus of the talk today, but this has a lot of economic implications as well. Right, this is basically when more customers are joining, this is how you are affected, and you see this very non-linear behavior. If you want to think of externalities and so on, a new customer joining is doing a lot of damage to others in a congested system.
Why is it called utilization time?
Utilization level?
Sorry.
Because it also turns out that this rho is also exactly the probability or proportion of time that the server is busy. So 0.9, it's working 90% of the time and 10% idle. So it really reflects how utilized the server is. Okay, so moving on to an economic model, the classical simple models for strategic behavior in viewing. Paper in 1975 by Edison and Hildebrand. So they considered MM1Q as like in the previous slide, Poisson process with rate mu and exponential service time with rate. Poisson with lambda and service with rate mu. But now every customer that obtains service has some value or reward for service R. It's a nominal value, but they also incur waiting costs for every unit of time that they spend in the system. So, of course, we want to avoid waiting, but we want the service in the end because it has some value. And in this model, customers need to make the decision before they join. They do not know the queue length. There are also models like that, observable models, we'll call them observable models. So here it's in the unobservable class. Every customer must decide without inspecting the queue length. Okay, so action set here is join or block, and that's two options. And the strategy, of course, is just a single probability, the probability of choosing action join. Okay, so this is the game. Note here that it's in terms of a game mode, this is a bit non-standard because what exactly is the population of customers here? Like it's not a finite population, of course, but it's rather an ongoing process of arrivals which all make decisions. So
this has a name, it's called a random player game.
Not exactly. Random player games usually have a finite. The number of players is follows some distribution, but it's finite with probability 1.
Well, actually, I wrote the paper.
Yeah, I know that paper. Even cited in words, but what I mean, in your setting, correct me if I'm wrong, there's some random variable for the population. Often it's Poisson, and it's but it is finite with probability 1, right?
It's a point course.
But is the population finite, or it doesn't have to be? So maybe I'm thinking of another one of your papers.
Yeah, so but one model is that there is no population.
Okay.
So just the players will just come in there.
Okay. And continuously.
It can it can be also just like that. So it can be.
Okay. So we have to talk a bit more about it, but I mentioned
this is the Poisson process.
Yeah, here it's a Poisson process.
So that's
but the point is that it continues indefinitely. So in this sense, it's a bit like a non-atomic game, like where every single customer has infinitesimal effect on the system itself and the utility of others. Yes, this is one way to think about it. And another way to think about it is, I'll mention a bit later, but I'll be happy to hear more about that. But I think there is no really agreed upon standard convention of what a queuing game is in the game theoretic sense. But for this model, it will be clear in a couple of slides how exactly the game is defined with respect to the customer. Okay, so because this is an MM1 queue, we have this very nice formula. Give me a strategy P that all users are. How do I move the cursor there? Okay. Yeah. So we are given some joining probability P. The arrival process is still a Poisson process, but a thin one with great lambda P, and this is the expected delay. Of course, if lambda P is smaller than the service rate. So we can compute so think of now a fixed one customer and let them ask, well, everyone is playing P, what should I do? We have this simple expression for the utility, the reward minus the waiting cost. And we assume that not joining means zero utility. Of course, without loss of generality, it will be some other constant. And we denote the best response to P by as a set value function that responds to P, and it's basically specifies join or not or randomized. And of course, randomization is only optimal if this is exactly zero. Right? If customers are indifferent between joining or not, then that's the only situation where randomization is possible. Otherwise, if it's positive that they want to join, if it's negative, they don't want to. They both. Okay, so then the Nash equilibrium is defined with respect to the best response function as usual, where all customers are getting a best response. Okay, so we got around the issue of what are the players by looking at this stationary utility and enforcing basically symmetry. That the Nash equilibrium.
You said that they do not observe the Q state.
Yeah, that's
basically. Right. So, but they know the parameters, the C and the lambda?
Yes, they know the parameters. They know
okay.
C, R, lambda, and U, they know all of them. They know all of them, and they know what an MM1 Q is, and they can compute this expectation.
Someone assume all the players arrive somewhere in the middle. No one arrives first.
Yes, exactly.
Yeah.
So there is no knowledge about where you are.
Is this a realistic assumption?
If there's no knowledge, I could be number 3. So I thought that you're going to say that the time starts at -infinity.
That's one way to look at it. Yes. Or start at -infinity, or started at time 0, but as far as you are concerned, it already started in a stationary state. You're prior about it. The
stationary state depends on my action.
Yeah. So, yeah, okay. So there are some issues here. Right? So I think, especially if you think of it from a game theory perspective, there are some issues here, but this is how it was defined for these games, and I guess in hundreds of papers that follow. But
is it a realistic assumption?
Sorry, I didn't hear.
Is this a realistic assumption? I mean, usually you observe the Q. I mean, in any reasonable situation, you might get information on the Q length, but not on the parameters, right? Because this depends on like long-term statistics. So somebody tells you.
Yeah, if it's reasonable or not, I guess it depends on the setting. In some cases, you make a decision before you have any information of the Q.
Yes, you just don't even.
Yeah, so you again, this is very similar to transportation type model, where although today you have real-time data also in many of those settings, But I agree it's not reasonable for many settings. R and C, I think it's reasonable to, those are the customer parameters, so that's reasonable that they know. And mu and lambda, they know from past experience or some knowledge of the system. But as I said, this is not, this is 1975. This is not the cutting edge model for how to think of strategic behavior in a congested system. This is more for the talk to explain the kind of models we are looking at. So I won't try to argue that this is realistic.
Uniform R is maybe not unrealistic. Uniform for
Yeah, definitely. But but that doesn't make it much more complicated. Let's say a common distribution, some distribution here. You can do everything but one. Yes. Okay, so this is more the point of showing this model is really to explain what we are thinking about with a simple non-realistic one. Okay, so everything with respect to this stationary distribution. Okay, so equilibrium here is just finding a fixed point of the best response, right? And if we thought it looks like this for low levels of P, if the joining probability is low, I want to join. If it's high, I don't want to join. And there is exactly one point that makes me indifferent between the two. And it will be important later, but notice that inherently this type of setting, this best response is not continuous. It jumps between 0 and 1. Okay, so here we have all the formulas. So there's a nice explicit solution for the Nash equilibrium joining probability. And you can, and then they also, this paper also looked at how looking at optimizing social welfare by charging an admission price and various things like that you can do because of the nice closed form solution here. Okay, so this was all for the MM1, and for MG1 and GM1, where G now indicates that you don't make specific assumptions about the service or arrival distribution. Here the service is general, here the arrivals are general. We can still do computations, maybe less explicit, but still more or less get compute the Nash equilibrium in closed one. But what about the GG1 Q? Okay, so if I don't think anything is Markovian, not arrivals, not service, so this is not possible anymore because the GG1Q it has a stationary distribution under the same stability condition, but it's not explicit. You can't say anything about it. You can't compute probabilities or expectations or generating functions. There's just no closed form solution for it.
By closed form, you mean that the closed form uses the distribution function? It's written in terms of this distribution function.
What is written?
The solution.
You're talking about the equilibrium, or
You said there's a closed form solution.
no? There is no close.
No, for the first one.
Oh, for the first
bullet.
Yes.
So you have the distribution function.
Yeah. So in MG1 you have the Laplace transform of the waiting time, so you can compute expectations depending on the moments of G. In GM1 you also have a representation that you can talk about the transform and expectations at least with some form. It's GM1 is not completely explicit, but still writing down an equilibrium condition and solving it is not too difficult. But here you can't even write an equation, find P that solves this. Up to maybe some messy integral function. Okay, so as I said, there are lots and lots of papers about queuing games with various information. You observe the queue, you don't observe, you know the parameters, you don't, you make other decisions. The book in 2016 cited about 800 works, and since then people are still working. Okay, so there are a lot of people working about these kinds of models with economic analysis, but almost all of them assume systems that you can do exact computations for, like the MM1 setting. However, as I said, for GG1, which is a completely reasonable model, right? You don't assume that everything is always exponential. You can do this, and many others, and many non-Markovian systems, and also Markovian systems. If I would tell you the MM1 story, but now I say there are two MM1 queues, and everyone arrives and joins the shortest one out of the two, right? Completely reasonable, like everyday model, where there are two stations, you join the one with the shortest queue. This is intractable. You cannot compute the stationary distribution. It's equivalent to some boundary value problem that there is no explicit solution for. So you don't need to make things much more complex to get a system where you can't, where exact analysis of the stationary distribution is impossible. But you may still be interested in finding the equilibrium in such systems. Okay, so this will be our guiding example in this talk. One of the models that we presented a solution in the paper. Think about a system with two parallel GD1 queues. Okay, so there is a common sequence of independent arrival times. That is, arrivals are a renewal process with some distribution h and mean 1 over lambda. And there are two parallel queues and physically located in different places. So you need to decide before you join which one you will, to which station you will go, to station 1 or station 2. And they both have some general distributions. And we assume that service time is longer in station 1. But in some sense, station 2 is better. Okay, and same as before, you get a reward for service, you pay for waiting time, and you need to decide now between two things, three actions, join Q1, join Q2, or both. Okay, so this is a very simple model, but completely intractable. Now, given distribution H, F1, F2, if I want to say to find the decentralized routing policy here, what proportion will go to station 1, station 2, and what proportion will not join at all. I cannot compute this. And this is because I know that stationary distribution exists for the waiting times. And not hard to show, given with the same stability condition, as long as the incoming rate is lower than the output rate, then these systems are stable, they admit a stationary distribution. If you assume a second moment, finite second moment for the service time, then the waiting times are finite, but we have no formula for this. Right, and now we want to do again sort of kind of indifference principle, make the waiting times equal in both stations or more, or if there are more stations, but we cannot compute this.
What is P1 and P2?
Probability to join Q1 and probability to join Q2. And P3 is the ones who don't join at all. Yeah. Exactly. Okay, so and it's very easy to show that the unique Nash equilibrium strategy exists here, but the problem is to compute it for arbitrary distribution. Okay, so we want to do this using simulation.
Yes, one question. The unique Nash equilibrium is for arbitrary distribution?
Yes. As long as this finite second moment holds for both systems. Mm-hmm. And you can even say even a bit more about its structure. We assume there's a faster queue here, so more so either everyone will join the faster queue or some proportion of the faster queue and some the other one, or it's the hierarchy here. And this you can prove analytically by monotonicity properties. But to find those P's, that's it.
If the two servers are identical, then it's solvable.
Well, then I think the solution should be half. Of the ones who join, it should be half and half. But the problem will still be to find how many join and how many join either of them. So it's still of the same level of difficulty. I still can't. I know that if they all join, it will be half, but what proportion will join at all?
This does not become the two points.
I know, because you still have this bulk option, which you don't know what proportion exactly. So it's half and half between the servers out of the ones who are joining, but you still need to say when the expected utility is exactly 0. That equation I cannot solve, even if they are the queues are symmetric.
Even for a single server.
Even for a single server. Yeah, this model is intractable even if there was just one. Yeah, that I still think
Because typically effectively next to the single server.
yes, that's right. It's of this it's basically the same problem as the for a single server, that's right. Okay, so we want to use simulation because stochastic models and we like simulation because simulation is possible for many systems that are intractable, but you can't say exact probabilistic carry out exact probabilistic analysis. Okay, so it's very easy to simulate GD1 queues. Right? Just give me 2 sequences of arrival as service time. There is a nice accuracy formula. This is a very easy task. And I can do this for any strategy team. And now if I run long simulations, I can get good approximations or estimators of the expected waiting times given a strategy. Okay, but still I want not just for a specific strategy, I want to somehow search the strategy space. So I don't want to, of course, it's a continuous problem. So looking for this 2-dimensional vector of P's, and somehow I want to try all strategies or traverse through them in a smart way. So I don't want to be, and I don't want to run very long simulations for many repeat different strategies. So what we do is we find an algorithm that does basically one long single simulation, and that uses stochastic approximation in order to adapt the strategy and hopefully converge to an equilibrium.
How are you affected by the non-continuity of your utility?
Yes, that's very important, and in a few slides, I'll show you how we deal with that. Yeah, but that's indeed you can't just ignore that because of course these algorithms so I'll present the algorithm and then repeat that question later if it's not clear in a few slides. So what we are using is what's called the Robbins-Monroe algorithm. So if you think of some function from Rk to Rk, for which you want to find root to take the data such that g data equals 0. But now and assume g is a continuous function, but it is unknown. You don't know its form. But what you can do is sample g, get observations of g for say you specify data, and then I give you an estimator g, which is unbiased. Okay.
What does that mean?
well, in our setting, think of the waiting time given a strategy. I don't have a formula for it, but I give you a strategy. I can maybe you through a simulation get an estimator for the expected waiting time by looking at some average or so. And so, but this is in general. Suppose there is some function g that you do not know its form exactly, but if given a specific point, you can generate an estimator.
What does unbiased mean?
This one, equality here, that in expectation it equals the function in expectation. So there's a classical work on these algorithms for think about the regression model, right, where you have y equals some beta 0 plus beta 1x plus noise, right? So so you don't roll, so you observe y's, but you may not know beta 0 and beta 1, right? But if noise has a mean of 0, that you get basically an unbiased observation of y. It's noisy but biased, but unbiased. Okay, so basically, so yeah, that will come later. But you can think of you observe you observe g theta plus some noise term. So here there'll be very specific structure, but in the classical notation that you basically observe g plus some noise. Okay, so the algorithm, it's like it mimics stochastic gradient descent algorithm. Basically says, well, if moving from the strategy or the value in the nth iteration to the n plus 1, you do the following: you simply take this this new estimator, multiply it by some constant, and update its g value. So Gn is a sequence of estimators for G. Sequence of unbiased estimators. Okay? And since they are unbiased, you expect this to be around the true point. Oh, step out of right around the true parameter data here, you expect this to be around 0, but it's not mean 0, so that's the idea. In many cases, G is in fact a small g here is a gradient you're trying to evaluate, but with some noise. Right. So that's a
but you need that gamma doesn't converge to 0 too fast. It should be like something like 1 over n, so that gamma n squared converges.
Yes, exactly. Yeah. Indeed. So with some conditions on G on the sequence gamma, you have a lot of different convergence results for these type of algorithms. But essentially, they're trying to mimic the gradient descent algorithm.
I'm not sure how the algorithm works. What do you do specifically?
So so at iteration n, you have your theta n. Now, with this theta n, you generate an observation Gn, which is an unbiased estimator of small g theta n. Right, so the Gn theta n is g theta n. So if this is far from 0, this algorithm will somehow
Works only for theta n?
no, for any theta. But I mean, iteration n, this is what's happening. So if say this is very far from 0, then you move away. Now, if g is some convex function with a single, where g is the small g or no, it's that that you are it's a sequence of g's. Right, each time you're generating a new observation given theta.
How important is the gamma n?
If Well, it needs to converge to zero, but not too fast. This will be explicit. Say, typically it's 1 over n. Because you need a kind of low large numbers behavior here for this term.
You said the capital G is a function, but I thought it's a random variable.
It's a random variable. It's a random variable. It's a random variable, but its distribution depends on data. Right, so for big data, it has a different expectation. Oh, maybe I hope it will be a bit clear in the queuing model where I construct a really specific object.
But why don't you have a sequence of estimate this?
Because you are changing data all the time, right? You are trying to solve this equation.
Right.
Right, you can think about the simplest case where about the G, think about the G that looks like this. This is theta and this is G theta, and you want to find this theta 0 point. Right? But you don't know that the function looks like this. What you can do is say sample it here, call this theta 1. So you won't get exactly this value. You'll get maybe some noisy d theta 1 plus noise. So you'll get some noisy observation of this point. But so what the algorithm would say in this case is that, well, so here you are very far from 0. So I guess this can be modified to the constants, but in this for this setting you want it to be negative, the contribution here. So here you don't know exactly where you are, but you feel you are far from 0. So you want to take in the next iteration a lower value. Okay, so the next iteration will at iteration 2, you'll get here, which here will be theta 1 minus the constant times this this noisy observation you had here. Okay, and if you are and hopefully when you are around 0, you get the fluctuation will stop and the algorithm will converge. Even you can think about, right, even if there was no noise, this algorithm makes perfect sense, right? It's just a gradient descent algorithm.
Gamma need to be positive?
No. I think so, yeah, there are many versions. Yes, there are many versions, and for a specific context, you need to construct it.
My question was about capital G. Why is it not the same in every iteration?
No, look, if you sample this iteration, your capital G will be a random variable that this isn't mean, but the theta 2 here, it will be a random variable with this mean.
It's the same function, which has not a different value.
Well, it depends how you model the noise. Maybe I should have specified something more right.
You say the noise may depend on theta?
Then not everything can depend on theta. So I want to say G theta. One way to think about it is like this. Okay, so
that's the same for every.
No, that's
yeah. In this case, it's the same for every, but it doesn't have to be. Yeah, it can depend on that. So maybe this was redundant in this setting, but it can depend on everything in principle, and there are various conditions. But let's proceed, and we'll see the algorithm again for the specific use here. Okay, so these kind of algorithms have been used a bit for optimization of queuing systems, but more in settings where they want to optimize the service rate, and then and the issue was really estimating gradients of measures like the waiting time and things like that, and then there you need gradient estimation techniques, so it's quite different. And there are some more that use similar kind of algorithms for processor sharing games, where customers need to make some routing decision. And there's recently a lot of work with reinforcement learning and neural network techniques where they are kind of similar because they look for solve fixed point problems, but of a different nature, with optimization and Markov decision process type of goal, where customer behavior is in a sense deterministic. But so what we want to do is present a general framework for finding Nash equilibrium in computing games. Okay, so after almost an hour, we're ready to present the model itself. So what we consider is okay, what motivation at the end of the talk. I will do the writing process. That is, I think the write times are IID. They all follow some common distribution. Every customer chooses an action from a finite set. So that is the strategy space is K minus one dimensional syntax. With randomization between the actions. We assume we denote the system process, which can be queue length, can be waiting time, but say networks or bigger in other systems, it can have a more elaborate structure this extent. But this is always the system state at the end arrival given strategy P. And we assume a time at the system starts empty. Okay, and we assume a regenerative structure for this system, which basically means that once in a while you return to an empty state. Where empty can be zero queue, zero workload, or all servers are idle. It depends on the system. But there is a zero state, and when you return to the zero state, everything starts again from a probabilistic perspective. Okay, so it's not need not be a Markov process, the GG type of queues. It's
What distribution of N should be XN rather than X1?
yes, thank you. Yeah, this should be XN. Yeah, so an L is a cycle length, is a time until the system is end. And between successive instance or the number, sorry, it's all discrete. It's all discrete. It's all in terms of arrival. So the number of arrivals until the system is empty again.
This is a random variable.
Yes, this is a random variable. You can think of it as a busy period of the queue. The time between the time it takes for the queue to empty since it starts.
It's the first time that the system returns to zero?
Yes.
Okay.
And we assume that it has a finite mean, and this is a necessary and sufficient condition for positive recurrence of the process and the existence of a stationary distribution.
And what's L superscript K?
And it's a kth moment of the bit cycle. Okay, so basically this is a regenerative system that is stable. And now, the utility of a customer is affected by three things: a state upon arrival. That's, I think, in the example, it was a waiting time. Can be some additional random outcome, say your own service time, for example. And P is a strategy that used by all others. Okay, so both V is just a vector of utilities associated with all K possible actions. Right, so in the example we saw before, the join both model, joining gives you a reward R minus the waiting time cost time your time in the system, which is the system state plus your own contribution of certain time, whereas that alternative is zero. Okay, so for every action given a system state, you assign some utility. Okay, and we know the utility vector UP as the state expectation of this V value, this V value with respect to the stationary distribution of the system, where we assume that the system is based on stationary distribution. Okay, so for every strategy, there'll be some other distribution here inside for XP, and V will depend on that.
You had capital X N, and now we have just capital
Yeah,
X.
so X is a stationary version of that. That's a long run. This is the long run average of the system. Okay, and again, this is the vector. So this gives you in stationarity what is your utility from your average utility from every possible action.
So the customer does not know the time,
The customer
and
he
he
does not know
N.
who does not know it. A symmetric Nash equilibrium is well, one way to define the best responses say that you are using the R max of UP times Q, or your maximum over strategy's Q, right? And this is true because we are just optimizing between discrete actions, and you give positive probabilities only to actions that give you exactly the same utility. Right? So there's the indifference principle working here. And indeed, this thing is not continuous. So what we do is consider another best response function, a smooth version of it, which penalizes deviation. Okay, so my best response to P, instead of just looking at this, I'm looking at the Q that maximizes this with the additional term that smooths deviation. Now this is a nice quadratic function, so it has a nice first order condition. You take a derivative, you solve for Q, you get this. So
What's the target?
transpose.
Sorry.
Yeah, no derivative. Yeah. So I will call this a target best response function. Take this, solve this optimization problem, but project it to the syntax. But you might, if you just solve it, you might get strategies with probability bigger than 1 or smaller than 0. So move it back to the syntax. Right. So if we look at the model that we had before with this best response function, this moving operator that makes the function look like this. But as you see, nice in the diagram, they share the same fixed point. And right, this is not coincidence. We can show that basically, if you use this FP as the best response function, it's an equivalent condition for the Nash equilibrium. And if you make some more assumptions that U and LP, the expected cycle length, are continuous, then a symmetric Nash equilibrium always exists and is given by this fixed point of the surrogate best response function. It doesn't say that it's unique. So, and this is one of the difficulties here. We impose no uniqueness conditions, but there is a Nash equilibrium always exists in this setting.
You can assume that small L is continuous, but what the recent assumption entails, it depends on the model.
Yeah. So indeed, it depends on the model, but since it would be very hard to come up with a Turing model that does not satisfy.
Does it cause any problem with the unbiasedness condition in the stochastic optimization?
Well, I didn't define the algorithm yet, so let's
okay.
So let's wait a bit with that question. I think that's definitely an issue. So I don't understand. Let me know.
35 minutes.
Okay, that's plenty of time. Yeah, okay, so this is just another way to characterize the equilibrium. So now if we could compute U, so now we could best response type of algorithm for computing P, for computing an equilibrium would be just to iterate on the best responses. Right? So just for every P, compute the best response and then update P and so on, and just do best response dynamics, and hopefully if things are nice enough here, this thing will converge. But as I said, in this context, we don't know U. U is some tractable function.
The example n comes from giving different weights to the penalization term. So is when you penalize by subtracting the difference between P and Q.
Yeah.
And if you weight that, you get your gamma n with just a more general.
The choice of gamma n?
No, I mean gamma n is not more general, it's just the weight that you get to the cost is 1, and now you change to gamma n and everything goes through 1.
If you think, you mean if you will make a fixed gamma?
My question is not clear, then you just talk about it.
But yeah, in the deterministic case, you don't, you could even you have more. You could keep gamma fixed, and it will still converge. That's what you mean in some cases, depending on the functions. But in the stochastic case, it will be very. Okay, so cannot evaluate UP, so we use simulation to get an estimator of it, and this is our algorithm. Okay, so strategy at iteration n+1 is the projection, right? That's coming from the surrogate best response function of Pn plus gamma n and some observation Gn, where Gn. I didn't define it yet what it is, but it will be an estimator for this value, GP, which is the UP multiplied by the cycle length, mean cycle length with respect to the strategy P. And here we come to the issue of the question that was asked that we cannot estimate UP directly without bias.
What is this small g? What does it stand for?
Well, it's just the expected utility, the one that we want to evaluate, but multiplied by the expected cycle length, expected busy period for strategy P.
Why?
This the reason is that what we are doing is that we are generating the system for a busy cycle until it empties out again, and then we are taking the sum of all utilities faced by all customers that arrived within this cycle. And if we just took this average, the average utility here, we would get a bias estimator because of the length bias issuing something, right? When you say in long busy periods, you tend to sample longer waiting times, for example. And so if we just took the average of utilities and ignore the cycle length, then we get a biased estimator. But if we take this estimator as defined here, then its expectation is exactly this GP function. So from this simulation, there is no way to get an unbiased estimator of UP directly. So we need to scale it by its expected cycle length.
And then what do I do? Suppose
Okay, yeah.
I get G equals 0, so then E equals 0.
Yes, exactly. Yeah. So it doesn't change anything for the equilibrium condition. This you can push into even the gamma sequence in the end, this constant from a practical perfect. Yes, it does not change the fixed point condition. But this product you can estimate, and just UP alone you cannot get a non-biased estimate alone. Okay, so yeah, so this is the algorithm. And so let's just before taking the main results, look at the example to make the estimation step clear. So think of the model we had before, two GT1 queues where you need to choose between the two queues or bulking. So this is what the estimator looks like. So you sum over all J here represent the arrivals in a busy cycle. So there are L arrivals, each one of them. For each one of them, you compute a vector of utilities had they chosen this action. Okay, and it doesn't matter what they really did in the simulation. In the simulation, I'd say if there is a mixed strategy, assigning probabilities P1, P2, P3 for the different actions. So in the simulation, you will generate something and they will choose some action. But I'm not interested in what they actually did. I'm interested in pinpointing every arrival instance, what would have been the utility had they chosen each one of the possibilities. And I record this vector for the size of the action set for all customers and sum them up through the entire cycle. And this is RG. And this, as I said before, due to known results about regenerative processes, it has an expectation of exactly the GP function defined for the product. And implementing this, we see quite fast convergence to. So this is for, well, I don't even have the parameters here, but this was for some specific distribution. This is what it looks like. So this is actually the number of busy cycles we generated, and we see that it becomes less and less noisy, and the gamma n here was chosen of an order of 1/10. Yeah, so this shows that it works. But
You mean you can check that this is the Nash equilibrium?
yes, yeah. So if you have a candidate for Nash equilibrium, it's not hard to check whether again it will again rely on simulation, but with any level of confidence that you want, you can verify that it gives that the solution is a Nash equilibrium. Here it's very easy to verify that it works. But of course, we want some theory, more justification, or to characterize when it works. So we
you get a P that is not the exact Nash equilibrium. So what do you verify? You get a P. It's not the exact Nash equilibrium, right? And then you verify that it is what is
so for example, the test that you can do is takes the output P that you have, generates a system with a strategy for a very long simulation, and construct a confidence interval for the value of the utility at the strategy, and hypothesis test that is different from 0 or not. And since you can make the simulation as long as you want, you can get as high confidence that you want. But so again, it will be verification by simulation. You cannot compute this function. But if you believe in the CLT and I mean, it's accurate in a probabilistic sense, but this test. But anyway, we develop theory. We want to do conditions for when and what exactly does this convergence mean. Okay, so we make a few assumptions here. Okay, so this was already mentioned. We assume the cycle length is continuous with respect to P, and we assume that it also has a second moment for any strategy P, and So this is quite standard and generally holds for queuing systems, and it has to do with the stability conditions or existence of moments of the waiting time in queue. So these are kind of standard arguments. This is a more standard assumption. This is a more special assumption that you may need to work hard to verify that G itself, the sum over a busy period, is uniformly bounded within the strategy space. You need to assume something about the utility. So in this, I don't have a chance to really explain what's going on here. Like we know about dynamical systems is kind of like a Lyapunov condition of stability of a dynamic system, where this H is the gradient of the potential function. So again, these two you may need for specific models. You may need to work hard, but they are conditions that you can verify, and we did verify for specific examples. And you can make this much simpler. Remember, I didn't assume a unique Nash equilibrium. I don't want to start with uniqueness, because many times in these models you don't have uniqueness, so you don't want to limit yourself to unique equilibrium. But say utilities are convex and there's always a unique best response, and you can show the unique Nash equilibrium, then these things become immediate, this kind of stability condition for the algorithm. And the step size function, as I said, it needs to be a sequence that converges to zero, but the sequence converges, but the series does not. And in square it does. Right, so 1 over n is not for the immediate candidate, but also 1 over n to the power of alpha can have advantages in convergence rates. So these are, and this is essentially to get a law of large number behavior for your average estimate there. So with this condition, we show that the algorithm converges almost surely to a set of points that are equilibria. In this general setting, as far as we know, for arbitrary functions, you cannot guarantee that the algorithm will in fact converge. It may keep on moving within this set of equilibria. If there is a continuum of equilibria, it may fluctuate between them, but it will end up in a set that all of them are equilibria. If the set of possible equilibria is not continuous, if it's discrete, then it will converge to one of them, with probability 1. So as we learned during this process, we are not experts in a stochastic approximation. There are many subtle technicalities here in the convergence of such algorithms, but so this is what we got. So it's basically relies on that kind of classical results for this kind of setup. We also have a result about the convergence rate. So if you take gamma n the constant over n, then it is known that the algorithm converges at the square error or square distance from the actual equilibrium solution is the order of 1 over n. And then if you want to give the output some probabilistic economic interpretation, they think of an epsilon Nash equilibrium, where you want to say, well, everyone is this strategy is optimal in an epsilon sense, where your best response up to an epsilon. You can show that we can show that this happens with the probability, with a high probability, where high depends on n. Okay, so this gives you a quantification. If you have this algorithm for 10,000 iterations, you can be confident that you are this close to the equilibrium in the epsilon sense with this high probability. Doing convergence rate analysis for the more general setting it appears very challenging, but this is one result because of pain. And we have implemented this, and and then for various systems which are well multiple GD1 queues, like the example I described, which is a simple model that so far did not have any solution, and also to supermarket games, which are games where you see a lot of queues and choose between them. I mentioned this in the beginning. These systems are very simple and natural, but really hard to analyze. So we apply this to this as well. And other examples, also examples where you actually do have information, you observe the queue length, and then make a decision. And these are also very difficult, but with a slight modification, the algorithm works, and you can also allow customer types, and we verify conditions for convergence conditions for all but one of these examples. This one under some limitations. Okay, so these are all natural models where so far only Markovian analysis has been done. And in the end, the assumptions that you need for everything here boils down to the service time has 2 or 3 finite moments, things like that. So you're not really demanding a lot from the model. Okay, let's here. Yeah, so we modified this also for an observable game. You said at the beginning, quite right, that in many cases you do have some information about the system before making a decision. So we considered also this setting, and then you by considering some information function that from the system state you observe some signal, which may be the expected waiting time, which may be the exact queue length, or just something like there are at least 10 people in the system already. The information can be different, but we and if this function lives on a discrete space, then there is a natural way to adapt the algorithm. And just to give you some context for this observable model, even in the single server, the most simple example, this was actually the first classical model for this type of strategic queuing model was in Naor in 1969, where it just derives the optimal threshold for an MM1 queue. You see a long queue, you leave, you see a short queue, you jump. The NG1 model, it was shown that it's not necessarily a threshold strategy because the shape of the distribution G may affect your decision. For example, think of the hazard rates, a long queue may imply that service is about to finish. So you get strange things here, and notice the gap. And it's not because people didn't try. It took many years for people, and Yoav Kellner in the end gave full solution for this model for the ND1, and DG1 is completely intractable. Not only is a stationary distribution intractable, you also need to find the stationary distribution conditional on observing some information. So it gets very messy very fast, and we call the simple algorithm. I won't go into technical details here, but it's the same kind of algorithm, and this is the observable GG1 model, and it shows quick convergence to equilibrium strategies. Here you see a case where you don't have a threshold strategy. You see queue length 2, you randomize between joining or not, which is a bit strange, but it happens. Yeah. So I'll summarize. Stochastic approximation procedure for computing Nash equilibrium in games, condition for convergence. Basically, and the bottom line is that this can be applied almost to any system that can be simulated. Even if you cannot verify the conditions analytically, because it's a very messy system, if you apply the algorithm and it converges, you got an Nash equilibrium. Some convergence rate analysis and some flexibility as well to extend it to other types of models. Yeah, and we are still thinking about various things, relaxing assumptions, looking Also in cases where some strategies are unstable and then you need to detect stability somehow in the algorithm. But there, the danger is that you get busy cycles that never end for some bad strategies. So you need to modify it to stable. Stable, it means basically that the system becomes empty once in a while. Like the time it takes for it to empty has a mean.
Can you apply it when you have multiple classes of customers with different utilities?
Yes, but if they are discrete.
Yeah, but how does that affect the Q discipline? I mean, it's no longer a FIFO, right? The optimal.
No, I didn't assume FIFO in the general model. It doesn't have. You can have priorities. You can have different service policies. I didn't assume anything about the service policy. Those are just in the example, but in the general model and result, it doesn't assume FIFO. But if what happens, the case of customer types is very similar to the case of system information. In both of them, what you do really is run parallel algorithms for every possible type and every possible information you can see. So there are computational issues, but the idea is really the same. So non-FIFO and priorities and these kind or networks can introduce computational challenges in evaluating or estimating various things, but they still fit in the framework. Yeah,
because they quickly become NP-hard, right?
Yeah, so since it's not an algorithm, that outputs a solution, this is the optimal value.
No, but even the simulation
computation. So the convergence is probabilistic. So but so it's more a matter of the rate, right? It's not. There is no. The complexity goes through the rate, the probabilistic rate of convergence. It's not really in the number of computations. Because you never say this is the optimal value. It's always in the end an estimator. It's based on simulation. Yeah, so one thing we are now quite keen about is that you can also add a regulation dimension. Suppose you can charge an admission price. But again, maybe you don't even know the underlying distribution. Can you somehow play with the decision the control variable like price and simultaneously estimate the social welfare optimizing price or revenue maximizing price while satisfying the equilibrium conditions.
So you define the strategy of the customers and the strategy of the server pricing.
Yeah,
simultaneously.
Yeah, simultaneously. In every iteration, you change your price, and you can even change like you're just changing the price, and the customers themselves are doing some guest response. And hope if you do things right, this thing will converge to an optimal price while customers are satisfying their equilibrium conditions. Yeah, that's it. Thank you.
Thank you. If you have finitely many equilibria and you start at one of them, it's P0, will you stay there?
No, it's stochastic. There's noise.
So
Especially if your initial step size is big, then you will be paying for noise. But you will converge quite fast.
right, so this will give you some notion of stability of different equilibria.
Yeah. How could we quantify that?
somehow according to the basin of attraction or something.
Evolutionary stable equilibrium will seem to be
Or perhaps some of them are unstable, that is,
yeah.
you want stable.
Yeah, yeah, that's a good point. I don't really have an idea how to quantify that. The probability, say you start from an equilibrium, what's the probability that the algorithm will converge to the same initial point?
Mhm.
That's, for example, a measure you could think about. But I have no idea how you could characterize something like that.
So it's not just a matter of mathematics, it's also can give you some qualitative characterization of equilibrium.
Yeah.
That they mean differently.
Yeah, but even to know that there are multiple solutions, you would probably need to run it a few times at different initial points. But in the beginning, you have a model you don't know. You don't know if there is a unique, if there are multiple, if there is a continuum. So you can run it a few times and then see if you see it stabilizes in different places, then you can also empirically start to analyze these kind of questions.
The noise of the estimator may depend, and the noise of the estimator can be different in different equilibrium, right?
Yes.
So that's not fair in terms of determining which equilibrium is most stable. Yeah,
That's true. And that you can quantify because in the end, the convergence here is the type of law of large numbers. The law of large numbers for a dependent sequence with multiple various complications, but in the end, it's a law of large numbers type of result. But you can also construct a central limit theorem and quantify again something which will be a function of all the system primitives, but you can also quantify the asymptotic variance, the asymptotic normality around the different equilibrium points. So that there is a concrete measure to that's actually a very good point to which is related to the stability of different points. Although establishing a central limit theorem of multiple points is probably challenging. But if we get in the other kind of mixture between randomly, you can get to different points. Yeah. So technically, this can be hard, but you can try at least from simulation to evaluate these things. Okay.